All right. So last week we had a basic introduction to reinforcement learning, and we're going to be spending a good amount of time going into a much deeper dive on this. But before I do that, I just wanted to ask if anyone has any questions about doing, not necessarily with regard to these lectures, but the games that you are making. That's really the important part of what's going on the side here that I'm not checking in on a day-to-day basis. But does anyone have any questions or concerns about the game that they are making and the pace which we are going with that, when it's going to be due, what the expectations are? Yeah.
Wondering with we're working on repositories have like little prototypes for like games and stuff like that that'll be in our like mini game thing, but we tried to like push the repository to GitHub. It's like too big to like try to export.
Set up and get ignored. That usually means that you don't have a good get ignore.
Oh,
So there is a Unity-based get ignore that will ignore most of those large files and get rid of just about all of those problems.
okay, so
Any other questions? Any other thoughts?
Beginning of week 5, or just play test. It's supposed to be turned in the Sunday of week 4.
Yeah, the very end of week 4, beginning of week 5. Week 5 is going to be reviewing, so you will get your assignments for which games you need to play during that week.
How many games is each person going to be responsible for?
4. Yeah, you will play 4 games for at least 30 minutes each.
They're going to be like something on Canvas, like some kind of survey to fill out or something for those games.
Yeah, so there'll be a repository for reviews for each game, and you will submit a review to each of those repositories, and then we will collect those reviews for each game, strip your name off of all of your reviews, and pass them back to the original development team so that they get redacted feedback, name redacted feedback on their game. Then that will also be the week of the exam, so there'll be some exam prep happening on the site as well.
And what day are we planning on doing the demo? Friday?
Yeah,
So the exam would be on
would be Wednesday in place of this lecture class. Other questions? All good so far? Okay, we'll dive into it. So the reason that I introduce reinforcement learning the way that I do is that I want to make it as intuitive as possible when we start to dive into the deep details of reinforcement learning, because there are a ton of ways to customize how reinforcement learning works based on your needs, the size of your world. So we're going to see how so a lot of this material is pulled from the book that the original inventors of reinforcement learning wrote and came up with a second edition of not too long ago, which is very useful, very nice. We'll start with a little bit of review. So we talked about states and actions and rewards with regards to this agent environment interaction. The agent takes an action, one of the actions that it is able to, given the state that it is in, and that changes the environment in some capacity. The environment returns to the agent both the new state through its percepts, so how has the world changed since the time that I took this action, as well as a reward from a reward function about how good was that action. We'll talk a lot about how to construct rewards so that the task is learnable. Because if the reward function isn't any good, then that's what we're using to base a good action from a bad action and being able to tell that difference. A lot of worlds in reinforcement learning are structured in a way that is a Markov decision process, or MDP. Have we seen MDPs in prior classes before? Who's seen these or knows what they are? A couple people. All right. So really, it's just it's a transition graph where each state has transitions to other states based on something that is probabilistic. If I am in this state, then there is a probability that I end up in another state in the next action. So there are states. The agent will make actions. We will find those rewards, but it's a nice way of coming up with this. And we state those transitions through the use of a transition probability. So this tells us what is the probability of reaching a new state, we call that S prime, and the associated reward of that transition when we take a particular action in a particular state. And all of this is embedded in this data structure, the Markov decision process that we can see. The MDP is, you have full access to the world and you can see exactly how probabilistically the world works. So as an example, maybe if we're looking at the probability of flipping coins, since that's not based on an action whatsoever, the action is I flip the coin, and 50% of the time, the resulting state is that I've added 1 to the number of heads that I've seen, and 50% of the time, I've added 1 to the number of tails that I have seen. There's only one action to take, and probabilistically, you'll end up in one of 2 new states, depending on the result of that random coin flip. So we can state this by saying the probability of being in the new state and receiving this reward, given that where we started is in state S and we took action A. So first and foremost, does that make sense as a conditional probability? Given that we're in this state and seeing this action, that's just saying that we're looking at this particular state. Like, let's say instead of using a regular coin, I'm using a weighted coin, then the state is different. It's a different world that we are in with respect to that. So the chance that we end up in a new state with 1 more head or 1 more tail than we did before is going to change probability if we're in a different state. The probability of winning the game when we're close to the end of tic-tac-toe is very different than the probability of winning the game when we're in tic-tac-toe and the game has just begun off of a single action. So the state depends, the state and the action pair change how likely it is to end up in this state and receive this reward. Really just cause and effect. So the probability of that conditionally is just the probability that the states that we're in at time t is S prime, this new state. The reward that we get is some particular reward, given that at time t minus 1, we were in state S, and the action that we took was A. So it's just relating the variables that we see there to what had to happen for this to be the case. At time t minus 1, we were in this state. We took some action, and because of that, we ended up in state S prime. So what is the probability of that exact sequence happening? And then receiving that particular reward from that process. That'll be dependent on the reward function. But if we have access to all of this information, then we have the ability to analyze the environment and find more information about the environment, like the distribution of possible next states and rewards given the state that we are in and the actions that we have available to us. So we can look at taking out the reward. What is the probability that we end up in state S prime, given that we started in state S and took action A? That's just looking, we take the reward completely out of the function and say that at time t we're in S prime, given that at time t minus 1 we were in state S, given that the action that we took was A. Let's again make this a little bit more concrete. Let's tie this back to what we've already seen. We're in some tic-tac-toe game and we are close to winning the game. Let's say the last thing that we did is let's actually say X, O didn't move here, O moved here. That makes more sense. So this X hasn't happened yet. We are about to solidify that we are going to win the game by playing the X that is here. O cannot win the game after we play X here. But this is now the move that we're going to make. So the state S is right here. S prime is going to be after we make a move and after the opponent makes a move, we're going to be returned to us at a place where we can make another action. So the action that we would define is, let's just call this cell 3, 3. So if the action is to place an X in 3, 3, then the state at time t-1 was this snapshot of the board. And at time t, once we're ready to do that, we will have moved here and maybe O moves here. And now this is the state at time t once control has been returned back to us. So the state is again your snapshot. S prime is what happened after you made the action. You chose where to play. Your opponent also chose where to play. But you can imagine there's a probability distribution over this now. Are we guaranteed to be in this state when we make the decision, place an X in 3, 3? And the answer is no. We don't know where this extra O is going to be placed. It could be placed here or here or here or here. We're going to have an estimate of the probability distribution for how likely it is if we play here. What is the next state? What is the game going to look like when we get to play again? That's some distribution. It's going to be based on the probability that at time t, we're in this state, given that at time t-1, we were here, and we decided to play at 3, 3. So that's just some probability distribution over everywhere your opponent might go, might make a move. And in this case, in tic-tac-toe, it doesn't matter because on our next move, we can win the game. But we would learn this from experience. And it simplifies basically just to, we can now sum over all possible rewards. How rewarding is it that we get back control after the CPU player has played there? The reward is 1. We're about to win the game. What's the reward if the CPU player plays here? 1. We've won the game. We're going to win the game on our next move. It doesn't matter what the CPU player plays. So we'll be able to sum over all of the rewards times the probability that we're going to be in that to determine what is the value of playing here. Playing here wins us the game because no matter what, we're going to have, let's even say that the CPU player plays random. So we would have a 0.25 times the value of the CPU player playing here, because we then play here and win the game. Plus 0.25 times the value of them playing here. We win the game on the next play. And you can see that the sum of this, that given there are 4 copies of it, would sum to 1, which means that the value of being in this state and playing here is 1. We would backtrack that information all the way to this state that says no matter what the CPU player plays or does, we have a strategy to win the game. That would be inherent in the value of this state action pair. Does that make sense? Any questions on that?
The reward value is either 0 or 1.
It's whatever the probability of winning is in the end state. But we're going to backtrack and say that wherever the CPU player plays, we have a way to win. If they play here, then we can win by playing there. There's always a route for us to win on the next move. So it's an approximation of the winning probability from that particular position. We would learn that through experience. We'll go into that process soon. But wherever possible, if there's math or an expression somewhere on the screen, I want to do my best to make that make sense. So this is just the transition function of a markup engine process. Yeah.
You could quickly walk us through the decision to place the X in a different spot.
Yeah. So that would be a completely different action. You know that the given here is a state action pair. So we would have a completely different probability distribution of where your opponent is likely to go if we chose when it is our turn and this hasn't been done and this hasn't been done. So it's our turn, we don't move in 3, 3. But we've modified the given part of this, the state and the action. The state is the same, but the action is different. So because of that, it's a completely different probability distribution. If we choose to move, I guess the middle wins the game as well. But if we choose to move somewhere that doesn't guarantee us victory, then we would have a different probability distribution. Because now it's very likely that the CPU player plays a blocking move, and now they won the game. We've set ourselves up to lose because of this play. So the state action pair is in tic-tac-toe, how we don't come up with the values of states, we come up with the values of state action pairs. Because the value of the state is going to depend on what we do, how we would determine action selection. How would we figure out where we're going to move? But once we have an idea of where we're going to move, then we can look at that value compared to all of the possible states that we could see after the opponent plays. And that gives us a little bit more information. Good question. Anything else I could answer? Okay, so this can be looked at like a transition graph, and we'll get an example of that as we look at the recycling robot example. So here is a learning task. We're a recycling robot, and the states are really just how filled our battery is, and it's binary. Our battery is either high or low. This recycling robot can take 3 possible actions. It can search for a dirty room to clean, or search for recycling. If we search, we get a high reward because we are actively cleaning something up. The battery status could move from high to low or from low to depleted. The next action is to wait. That gets a low reward because we're not wasting the battery searching. So it's better to wait than do nothing. I guess than to do something else, to search if there's nothing to do. But the battery status doesn't change. If it's waiting, it's in stasis, I guess. Or you can recharge. Recharge gives no direct reward, but the battery status moves to high from wherever it was. So now it has to decide which of these actions to take in order to maximize its reward over time. If the battery depletes, it gets a -3 reward and the battery status is changed to high. Basically, this means that that robot died. The battery died while it was out in the middle of doing something. A human had to intervene, go plug it in. And we would like to automate this to the point where no human needs to intervene, but we need to come up with a reward for when that happens so that it learns not to strand itself and learns to recharge when it has reasonably low battery. We can see the state, high battery, low battery, the action, whether it searches or waits or recharges. S prime is the battery level after that action takes place. And we have a probability of how likely we are to be in that state given the state action pair. So we know that when we have a high battery level and search, we're not guaranteed to have a high battery. We're going to call this probability alpha, just so whatever probability it is that the high battery level stays high after it searches. It also may, when battery level is high and searches, get a low battery level, and that will happen probability 1 minus alpha. And here are the reward functions for each of this. And we need to figure out what the reward for waiting is in these cases. We need to figure out what some of these values are from experience. So we can visualize this as a graph. So our states are our vertices, our actions are our edges, and the weight of that edge is the probability of taking that or having that action transpire. So when the battery status is low and we search, we're going to end up high with probability 1 minus beta and getting the reward -3. Because if the battery dies, then the human has to intervene. If the battery status is high and we search, we either stay high with probability alpha or it becomes low with probability 1 minus alpha, and we get the reward that is the whatever reward for that search happens to be on average. So we again just see this as a transition graph. Yeah.
I thought the table had a start low, recharge, and go low.
I think that probability is 0. So there may be some edges missing where there is probability zero. Can't happen. Questions on analyzing this or what this means? So we will find that in a lot of cases, our learning tasks can be represented as such, just as a transition graph between where our states happen to be, what our actions can possibly be, and then what states we end up in as a result. Usually they're much more complicated than this. One task that we will also need to eventually figure out is how to design rewards. So in reinforcement learning, the reward is correlated with the behavior that it learns. You can imagine raising a child and completely changing your feedback function to that child based on the actions that they take. You could train a child to kill themselves if you give them a high reward for consuming poison. Why would you do that? It makes no sense, but that is, you could design such a world, and those would be the outcomes from your terrible design for a reward function. So how learnable a task is dependent on the reward function. So for instance, let's say you want to train an agent to solve a puzzle or to navigate a maze. In this case, every action that they take is always -1. And whenever they find their way to the exit, then the episode terminates, and the score that they get for that episode is how many steps, how many time intervals it took for them to navigate from here to there. The idea is a larger negative value, so -2 instead of -20, means that it took them fewer steps in order to get there. They pathed more efficiently. The agent would receive a higher score for being more efficient. So not every iteration of this maze is the same. There is no positive reward. We're never rewarding the agent, but the agent doesn't really care about the value of the reward. It's just trying to maximize the reward. If the highest score it can get is -10,000, it doesn't emotionally see that or recognize I'm only ever being punished. It's just, well, -10,000 is better than the alternative. So that's what I do, is because it is the least punishing action. From our perspective, that doesn't really matter. It maps onto a little bit weirder word problem, like I'm gonna punish you, child, no matter what you do, but I'll punish you harder if you do it wrong and less if you get it right. That seems morally terrible, but again, for the computer doesn't matter. So a system like this, where we want to optimize how quickly it does something, take every time step and give it a small negative reward at each time step. And it will eventually learn the difference between a run where it just circles around someplace for a while before eventually finding its way out. And that a better run will be to directly go to the exit. And now we have a way of comparing runs to each other. Some are better, some are worse, and learn what is it doing in the worst situations, what is it doing in the better situations, and try to learn action selection probabilities from that run information. If we're trying to train something like a terrain bot that's supposed to navigate difficult terrain, then we give a reward based on how much terrain it traverses before it falls over, or before it runs out of battery, or before that allows it to see a link between the actions that it takes and how much forward progress it made. The more forward progress it made, the better decisions that it made with what it had. Here is a recycling bot or a packaging bot or whatever we want to call this. And every time it does something successfully, we give it +1, and then it learns efficiency. So if this is a conveyor belt and packages are coming down the conveyor belt and it needs to take packages from this conveyor belt and put them on another conveyor belt, then we give +1 for each box that it successfully does, and it will learn how to efficiently take a box from one conveyor belt and move it onto the other. Because if you're doing a reward on a per hour basis, something of the sort, it'll receive a higher reward per hour if it is being efficient and not picking up the box and swinging it around a bunch of times before putting it on the other conveyor belt. Or something silly that should be penalized rather than rewarded as much. So the rewards tell you more what you want to achieve, The reward function says nothing about how to achieve it. The how is embedded in the data. As you are learning or experiencing, as you're gathering this data, the how to be efficient is embedded in that data. Tasks can be broken down into two major categories. The first one is episodic, meaning that this episode ends. Very much like a TV show, the story is broken down into episodes that themselves have beginnings and ends. So tic-tac-toe is an episodic game because you begin the game and eventually the game ends and you can restart the game. So an episode is when the game ends. A maze is also an episodic task that completes when you finish the maze. So how do we figure out how good a run through an episodic task was? We calculate what we're going to call the return. And throughout the class, we will call capital G the return. I don't know exactly what that stands for, but G stands for the return at time t of some episodic task. So this is just going to be the sum of the reward that it got for every action that it took at every time step up until this terminal time step, capital T. This is the time step that ended the episode. So in tic-tac-toe, this is your first play, your second play, until the play that ended the game, the last play that you made before the game ended, with a win or a loss, doesn't matter. But you would sum the rewards from every one of those plays, and it would become your return for the episode. So it just becomes the sum of the reward at time k for all time steps t plus 1 all the way to t. It's an assumption about what that reward is going to. It's an approximation of what that reward is going to be. We're at time t right now. This is going to say as things can possibly go out from here, what is the reward for that? So the return is kind of the expected reward that we will see for the rest of the episode. All right, does that make sense? Any questions on that? I have chat pulled up as well. If anyone remotely has questions, feel free to type and I'll occasionally check that, make sure that I'm addressing that as well. So these are episodic tasks. This is a task that ends. Do all tasks do that? What's an example of a continuous task? You might ask a robot to do something, but the process by which it is analyzing doesn't ever end.
It just kind of starts like this, but then there's no like termination. It just kind of continues.
Yeah. Any examples? What kind of machine would you do? Yeah.
If there was like a, that had to like sort boxes into one place and red boxes into another place. And the box would just continually keep coming and then it's just expected to learn.
Yeah, sure. So some episode that doesn't end. The example that I'm going to attach myself to is stock market analysis. There's no point where the stock market analysis, like looking forward, there's no place where it ends. It's like, all right, maybe when you retire, your particular agent should stop there. But in general, market prediction never ceases. So a continuous task can't easily be broken into episodes and just goes on without limit. So if this is the case, how do we modify this idea of we're in this state right now? How good will it be for us? How good is it for us to be in this state? In an episodic task, you can start to look ahead and there's this horizon, the end of the episode that informs us, here's where we should stop our analysis. We're trying to maximize the reward that we get by this ending point. But for a continuous episode or for a continuous task, we don't have that endpoint. How would we deal with that? We still want to determine which actions are better in this environment from this particular state. But if we ask to look out into the future, that's an infinite loop waiting to happen. It's never going to return to us because there is infinity out there to predict. What could we do?
Go back to the multi-arm banded, we have to revisit previous decision trees and options to see if it's still good or bad.
It's a good guess. Yeah.
Break it up in episodes.
You could kind of break it up into some episodes, like the stock market could be today, tomorrow, the next day, the next business day. etc. You could do something like that. There's something that works even better. Yeah,
What if, like, in a way, every time you receive a reward, that would be like the Austin, treated like the other event, so every reward they did themselves and so.
Kind of. At a very big step. So basically what we're gonna end up doing is discounting future rewards. This is when we talked about the time value of money and $5 today versus $5 in 10 years. The present rewards will usually matter more than rewards in the future. So we're going to approximate some kind of discount factor, the rate by which future rewards decline in value. And this will allow us to create a function that converges instead of diverges. If you're looking at summing all of the future episodes, all the future values out to infinity, that diverges. If you discount these values, then this will eventually converge. So this gamma is between 0 and 1. Something that is close to 0 or is 0 is going to say, I only care about the current reward. Screw the future, I'm maximizing just this single reward. A gamma of 1 now says a reward that I get in 10 million years is equivalent to a reward I would get today. I'm indifferent between receiving $5 now and some number of years from now, after which I am probably dead. So we very frequently use a gamma that is very close to 1, but is not exactly 1. Something like 0.99, 0.98, 0.97. And in one time step, a gamma of 0.98 would say that reward is 98% as valuable as getting the same reward today. If we're going to look up 2 time steps, then that reward is 0.98 squared times as valuable as receiving that same reward today. So we can see that as this sum ends up with an infinite number of terms, whatever that converges to is our return. Since we have exponential decay, that value will get closer and closer and closer to some value without hitting it. What is that value? What is the limit of that value? Questions on continuous tasks?
What's an example of something you'd want to use? What's representation of a continuous task?
Yeah, so I was using the stock market as an example. So something like the return tomorrow is 99% as valuable as the return today. I want to focus on what will make me the most money today. But if there's an opportunity to make a little bit more money tomorrow than I could make today, I'll just multiply it by 0.99. If that's greater than the investment that I could make today, I will not invest today and instead invest that money tomorrow when I assume that it will make me a little bit more money. But if it makes exactly the same, I will now bias myself to making that decision today rather than tomorrow because the discounted value of that tomorrow is less than the value of it today. So this just gives us a way to converge the return based on how valuable future rewards are compared to present day rewards. And again, depending on your problem, that gamma will change. If we're modeling inflation, it's one value. If we're modeling, I don't know, they change. We'll define a policy as just given that we're in a state and we have probabilities of selecting each possible action, what those probabilities end up being is defined to be our policy. So a random policy says that given the actions that we could take, we will choose randomly. But you may learn in a game like tic-tac-toe, it's not great to play randomly. In fact, it would be better if we could define a function that says, take as input a particular state that is a legal tic-tac-toe position. We should come up with a distribution of what moves should we make with which probability based on the state that we are in. So we're going to say, what is the probability of taking a particular action given that we are in a particular state? So again, drawing up tic-tac-toe, using the same board as before, what is the probability according to our model that we will make each of the possible actions? There may be a best action, which we choose to do with probability 1. We may want to add some exploration into this. So whatever we think is the best, we're gonna do it 95% of the time. And 5% of the time, we're gonna do something random. Any of those come up with a different policy as a way of mapping the states that we're in to the actions that we could take. Whatever that function is that defines the action selection process, that is a policy. How are we doing? Does that make sense? Questions on that? Yeah.
So this is like the policy was what we were working on yet, the last lecture.
Yeah, yeah. You come up with an algorithm to solve a problem. The algorithm that solves the problem becomes the policy. So the goal of reinforcement learning is to learn an optimal policy, the policy that maximizes your return from whatever it is that we're trying to do. And that return is going to be in terms of the reward function. So as we design a reinforcement learning agent, our goal is to design a reward function that makes it as easy as possible to learn an optimal policy so that through self-learning, this robot, this agent is capable of performing the best that it could via any policy. It's going to maximize the reward that it receives given the actions that it takes. So if this were a chess playing robot, then it would maximize its chances of winning. How would it know to do that? Well, it would have a giant map of all possible chess states and a map of what moves should I make in every possible state. That doesn't seem feasible. So there's a lot to come still. All right, so next question we might want to ask is, given that we are in a state, how valuable is it to be in that state? So we are playing tic-tac-toe, and we're in exactly that same state that we were in before. There's an X here, there's an X here, there's an O here, and there's an O here. So the state value function tells us what is the expected return from being in this state and following a particular policy. So that to be able to answer the state value function, we need to know and have access to the underlying representation of when we're in this state, how likely is it that we are going to make each of the 5 possible moves. So the smart move is to move in the lower right-hand corner. So maybe this policy says 80% of the time we're going to do that. 5% of the time we're going to do that. 5% of the time we're going to do that. 5% of the time we're going to do that. And 5% of the time we're going to do that. This would be an example of a policy for this particular state. And any reinforcement learning agent will be able to map any state to its policy. But we can now analyze how good it is to be in this state if this agent is this likely to make each one of these choices or each one of these decisions. Yeah.
That kind of brought up an interesting question. It's if you ran this and it was finding that like that's the best spot to go in, the middle spot is also equal good.
It is.
But whoever you're running here that's doing this might not refine that because it's finding
Right.
this one is working every time.
Yeah.
So it might be just missing that one.
Yeah.
Works because it doesn't need to go there.
Yep, and we'll talk about exactly how and why that happens in a lot more detail with regards to the algorithms that you can use for learning from this experience. But for coming up with the state value function, it's kind of a snapshot in time of here is the policy. But we can learn from this data and change the policy based on this. And we'll get into that. That's kind of one of the next things we're going to talk about is how to take this information and improve this policy based on the underlying data of analyzing this policy. So it ends up being a very iterative process. We're going to analyze a policy, then improve the policy. And with this improved policy, we're going to analyze it. And from that analysis, we can improve it. And eventually this process will terminate with an optimal policy. But for the moment, just imagine that this is the associated distribution and we want to calculate how good is it to follow this policy? How good is it to be in this state following this policy? So to do that, we need to take an expectation, this hollow E is just the expected value of pi represents policy. So the value of the policy is equivalent to the expected value of the policy. We take the return, given that the current state that we're in at time t is s. And expanding that out, then we need to apply our discount factor for every possible value that we could see from here on out. Using this discount factor, even for an episodic value like tic-tac-toe, this tells us that winning the game now is better than winning the game in 3 turns. So you can still somewhat apply it. But yeah, you just expand this onto, we're going to look at all possible rewards from here on out. If I make this 0.8 move, how good is that? That's going to return us some number of states. We can take the expected value of all of those states times the probability that we end up in all of those states according to our knowledge, and we can backtrack that to here and figure out if we made this move, here's how good that would be. Same thing for every other possible move, and you just weight it by how likely your policy is to make that decision, and you end up with an expected value of the value of being in the state. That value changes if the policy changes. So that's why we have a value, a state value function with respect to a policy. As soon as I move from this policy to the probability of moving in the top right corner is 1, everything else is 0, the value of being in the state completely changes. Even though I'm 1 move away from victory, my policy says never make that move. If I'm never going to make the move that wins the game from here, the value of being in this state is no longer good. Because I'm going to do something suboptimal from this state because of the policy. We would like to learn if we're going to do something bad, how can we improve what it is that we're doing? But step 1 of this is just analyzing how good is this state value function? How good is this policy from this state? People get a sense of that? Would you be able to calculate this, do you think? If I could tell you what the values were of each of the states that could come from this. So this would branch into 5. All the possible moves that we could make. And then this would branch even further for all the moves the opponent could make. But if you had a model for that, it's already too much of a branching factor for me to throw in any kind of exam, but these are all of the possible states that you could find yourselves in, but you'd be able to have the associated probability. What is the probability that we move in this top right square? That's 0.05. And then evidence would suggest that if we move here, the opponent moves in one of the 4 remaining squares with some probability distribution. Then we can apply this same policy to the end result of the next state and say, how good is it to be in this state? And that would depend on the states that come after. That would depend on the states that come after. That would depend on the states that come after. But eventually we would reach terminating states that win or lose the game. And from there we can backtrack and come up with an actual value for being in this state. There would be an actual value here. So let's say we win the game here, we win the game here, and we will lose the game in other places. So the value of the state would be 0.85. We win, we win, we lose, we lose, we lose. And all of those were guaranteed in a single move. It's not actually the case. But if each of these led to a terminal condition, then we could backtrack that to here and say we're going to win 85% of the time that we're in this state, according to this policy. If we make the 80% selection, we win. This 5% selection, we win. Otherwise, we lose. How are we doing?
You give us some practice problems?
Yeah.
Okay.
Yeah.
Not necessarily in class, but I mean,
Yeah.
if you're gonna assign it for a test question.
Yeah. I'll find something for us to work on. Okay, questions on state value functions? So that tells us how good it is to be in a state. There's also the concept of an action value function, which is how good is it to be in a state and having taken a particular action. This is the concept of the exact same tic-tac-toe state. But now instead of analyzing this state with everywhere that we could move, we're going to pair it with a move that we've already made. So if we've identified this as the next move that we are going to make, we've gone through that action selection and it returns this move. How good is it to have been in this state and made this move? That's going to start with the question of, well, what state are we going to be in when we have control again? We know that our opponent has 4 potential places to move. So we don't know which of those we're going to be in by the time that we have the ability to make a decision. So we need to start with the reward given the state and the action. The expected value changes because the first thing we're doing is not following the policy to make an action selection. We've already made the action selection. The first thing to consider is what are the set of states that we could be in once the opponent makes a move. So Q is our state action function. So the state action value of this policy is the expected value of the policy applied to the returns, given the information we have is not just a state, we have a state and action pair as what's given to us. And it turns out that different scenarios or different settings make a lot more sense to relate in terms of state value, and some make more sense to relate via state action value. So it's worth knowing both how to identify from the state and the state action perspective. We'll see that when we learn some of these algorithms, but breaking this down, anyone want to take a shot at describing what this means? We wanted to take this, break it down into its components. What is it stating?
Basically, it's summing up like the resulting output of an action determined by the starting state and determining if there's a value to be had in performing that action and what state it could lead to.
Yeah, so if we've made this the very first, there's a branching factor. Before there was a branching factor of 5, because we had to look at where are we going to move as a potential. Now it's just, we're starting with the opponent moving in one of the 4 places. Given that, how likely are we to be in each one of those? So we need to sum up a discount rate applied return for every move that comes from here, but where we're beginning our analysis is no longer based on the state, it's based on a state action pair. We've already made the decision to make the move. But yeah, this is still just summing all future rewards discounted by how far into the future they are. We can do all of this with no experience if we have a full understanding of the associated world and probabilities. If we're not playing an opponent who acts randomly, if we're sampling from a world and we know the associated parameters, we have the ability to just calculate the state value function or the action value function. And we do so with the Bellman equation. So this just defines the recursive relationship between the value of a particular state according to a policy and the value of potential successor states. So if this is tic-tac-toe, this is deciding which move to make, and these are the places your opponent could move. So by the time you have control again at the next state, you don't know exactly which, but you would have a knowledge of how likely it is to end up in each one of those positions. And if you have that knowledge, then you can calculate everything, which is wonderful. So the value of this state is based on the probability of ending up in each of these states times the value of being in those states. So that's going to be inherent in this function. This is saying that the value of being in state S, again, state S is that top state, is the sum over all possible actions. So it's saying for each action that you could take, and again, whenever you see a sum, just think of this as a for each. Makes your life a lot easier. For each action that you could take, what is the probability according to the policy that we're going to take that action given that we're in state S? So how likely is this move? Maybe this move we will take 40% of the time. We'll take this move 30% of the time. We'll take this move 30% of the time. Now we have an ability to throw that directly in. For each action, one at a time, we're going to calculate the probability of taking that action from being in this state. And we will multiply that by the sum of for each possible state we can reach and the reward of being in that state. That's each one of these down here. What is the probability that we end up in that state and how much reward, how good is it to be in that state? How much have we improved our chances of winning in tic-tac-toe, moving from S to S prime? If we take this action, which we take 30% of the time, and then we end up, given that we took this, maybe it's a 50-50. This happens 50% of the time. This happens 50% of the time. Your opponent moves randomly, given that. We would now be able to calculate if the probability of winning here is, I don't know, we'll call it exactly 50%. And the probability of winning in this state is now 70%. And the probability of winning from this state is 30%. We can now have everything we need to plug in everything here and solve, at least for this path. If we took this action, which will take 30% of the time, then for each possible state that we could end up in when the opponent moves, given that we were in that state and took that action, we take the reward that we got plus the discount rate, discount factor being applied to it being one turn later. So that allows us to basically solve, once we have values for all of this, it allows us to solve this and come up with an actual value of being in this state. Does that make sense? Note that these don't have to be terminal nodes. Man, I got way too excited. We're over time already. So we'll come back to this tomorrow, but I guess in general, how do we feel? Yeah. We'll come back to this tomorrow.
So there's two problems.